Hello everyone, I'm Karanjit Singh from Group 2D, and today we are going to present you integrated project of semester January 2020. The problem statement of this integrated project is that we are required to maximize the production of hydrogen gas by using the SMR technology and at the same time minimizing the amount of carbon dioxide gas is released into the air.
So now I'm going to discuss the reaction engineering part. So what is the type of reactors and catalysts used? For SMR, packed bag reactor will be used, and the catalyst is nickels. For WGS, the reactor is also packed bag reactor and the catalyst is copper. Why we use nickels and copper? Because they are more cheaper compared to other catalysts such as platinum. So the descriptions on how to choose the reactors. So we have SMR and WGS. First, the methane from the natural gas will mix with the waters inside this SMR and produce carbon monoxide and hydrogens. The product of SMR will flow to WGS for further reaction to produce hydrogen gas. So how are we going to find the data? So the first step, we need to find the kinetic data for SMR and WGS. The order for SMR is 0.3 and this one is the constant, and for WGS this 0.6 is the order and this is the constant. And step 2, we need to calculate all the necessary index. So we need to base on these stoichiometry tables to calculate from the WGS. From the question that we know that we need to calculate for 30,000 tons per year. So we convert, this is after the convert, and we will get all the index. So from previous calculations, we will have expand factors 1.8 and conversion is 0.8. Based on these stoichiometry tables, we will calculate all the inlets for the production stream. And this is all the inlets of SMR and the outlets of SMR to WGS.
Total hydrogen can be calculated by adding the hydrogen from SMR and hydrogen from WGS reactor, and therefore we can obtain 472.16 mole per second of hydrogen. It's proven that this method can produce 30,022.124 ton per year. That'll be a little bit more than 30,000 ton per year because we only took 2 decimal places in our calculation. Next is the strategy to maximize the selectivity and yield of hydrogen gas and minimize the side reaction if there's any. The formula given for yield is flow rate of product divided by initial flow rate minus the final flow rate, whereas for selectivity it is flow rate of desired product divided by the undesired product. The strategy required for both SMR and WGS reactor is almost the same. To increase the yield in SMR reactor, the flow rate of reactant should be decreased because the flow rate of reactant is inversely proportional to the yield. This is because once the flow rate of reactant decreases, they will have more time to let the reactant to stay inside the reactant for the reforming process and more hydrogen gas will be yield. Based on selectivity, if you want to have high selectivity, we need to supply high concentration of methane at high pressure without inert. Therefore, PBR is used to make sure the concentration of methane drops progressively throughout the reaction. Now, to minimize the side reaction, the reaction is a reversible process. Based on Le Chatelier's principle, water must be supplied in excess. The reaction is more favorable to react forward, which is producing the product that is carbon monoxide and hydrogen gas. By this way, the reverse reaction will not occur. For the WGS reactor, to increase the yield is the same strategy, which is decrease the flow rate. Whereas for the selectivity, we need to supply high concentration of carbon monoxide at high pressure without inert. And to minimize the side reaction, we have to supply the water in excess again for the side reaction to not occur. Proceeding to the optimum operating condition and sizing of the reactor. For the SMR reactor, the optimum temperature is 500 degrees Celsius, and whereas the pressure is 180 m. The volume of the catalyst can be calculated by using the formula given. Based on reference, the optimum L/D ratio is 3, and therefore the volume of reactor can be calculated by using the formula pi d square L/4. Moving on to the WGS reactor, the optimum temperature is 280 degrees Celsius, whereas the pressure is 180 m. The volume of catalyst can be calculated using the same formula, and the volume of reactor can be calculated using pi d square L/4.
Assalamualaikum and good day to all lecturers and my fellow groupmates. I am Siti Farhin from Integrated Project Group D, and I will be presenting about separation process 2. These are the questions that we are required to answer, and I will be explaining for the first two questions. So in this experiment, we are using zeolite 5A as an adsorbent. In order to find the type of adsorbent, the equilibrium adsorption isotherm were obtained experimentally for a binary component hydrogen-methane mixture to test on two types of adsorbent, activated carbon and zeolite 5A. And in this experiment, the conditions are varied as the temperature are ranged from 303 Kelvin to 383 Kelvin with pressure range from 0 to 4 MPa. Result shows that zeolite exhibited better adsorption characteristics than activated carbon as we test on four types of properties. One is mass transfer, second is affinity, third is selectivity, and fourth is adsorption heat. For the first one, mass transfer, it favors in zeolite. As we evaluate from the graph of the adsorption equilibrium isotherm for the system hydrogen using activated carbon and zeolite 5A, it shows that the longer the equilibrium times, the slower the diffusion or permeation in pores. And activated carbon has greater equilibrium times, which indicates less adsorption efficiency of hydrogen. Next is affinity. It favors on activated carbon as we evaluate the graph of adsorption equilibrium isotherm for the system hydrogen methane using activated carbon and zeolite 5A. The steeper the slope of the graph indicates stronger affinity for the component with adsorbent used, and less affinity is preferable in order to reduce the reaction between hydrogen and adsorbent used. So the graph above shows that the activated carbon contains less affinity compared to zeolite. The third one is selectivity. Selectivity is also favored in activated carbon because in graph of effect of gas phase hydrogen content on selectivity ratio of methane to hydrogen at 303 Kelvin, the selectivity to adsorb hydrogen favors to zeolite 5A compared to activated carbon. Hence, we prefer a low selectivity of the component on the adsorbent in order to achieve our goal. And last is adsorption heat. It favors to zeolite 5A because the heat of activated carbon adsorption greater than the zeolite 5A, and higher adsorption of heat results to more diffusion breakthrough curve, which result in worse separation. And next is the type of isotherm that we have acquired is Langmuir isotherm. So the equilibrium data for zeolite 5A is acquired with a constant temperature, and this data is used to plot the graph of the concentration of solid in solid Q against pressure P, which is recorded to test on Freundlich isotherm and Langmuir isotherm. The graph of Q against P is plotted in order to identify what type of isotherm, and based on the graph, the curve fit Langmuir isotherm the curve fit Langmuir isotherm compared to Freundlich isotherm. On the side note, experimentally, the partial pressure and temperature for hydrogen methane component depends on the expected value relation to the gas property, and the component's vapor pressure must be greater than the component partial pressure to avoid condensation gases on the adsorbent. And the results show that multilayer is unlikely to occur. The relative error has been calculated, and the relative error for Langmuir is 1.03%, while for the Freundlich is 1.53%. Therefore, the best fit was achieved with Langmuir equation. Next, we go to the design of adsorption column. So to obtain the dimension of mass transfer zone, MTZ, the value of height of adsorption column and its diameter should be obtained. And these are the characteristics of the adsorption column. For the column height, it's 1 meter. For radius of the column is 0.07 meter, and the diameter of the column is 0.14 meter. So the graph shows the graph of C over CO against time that has been plotted, and from the information above, the value for TB is 3.25 seconds and TD is 12.2 seconds. Thus, the amount of TS is 6.15 seconds. Next, we calculated the amount of HB, and the value of HB is 0.52 meter. While HUNB, which is length of unused bed, we calculated for HUNB and the value is 0.475 meter. Hence, the dimension of MTZ is 0.475 meter, as HUNB represents the MTZ.
Moving on to our next point, which is the strategy to achieve 99.9% of H2 production and the desorption or regeneration process. The hydrogen is extracted and filtered during the pressure swing adsorption PSA cycle at a pressure above the level of the feed, while the absorption impurities are removed by reducing the pressure of the column. Therefore, in this cycle, we are using two columns, which is column A and also column B of PSA. The column characteristic and pressure operating condition of PSA column are stated as below, whereby in column A, the column height is 1 meter, and also while the column B is 8 meter. The column diameter for both columns is 0.14 meter. The pressure feed for both columns is 10 atm, and also the temperature feed is 25 degrees Celsius respectively for both columns. The feed of this cycle is gained from the process modeling and simulation process calculated in the PMS part, whereby we get that the feed is 962.375 mole per second, and the composition for H2 product, the H2 is 0.491. As we calculated, the in the question stated above, the production of H2 production need to be 30,000 tons per year with the 99.9% of H2 purity. Well, as we calculated, the 30,000 tons per year is also equals to 472 mole per second. 472 mole per second is the flow rate of the final H2 production. To calculate the efficiency of H2 production, we need to find the useful product and also the total input product times with the 100%. Therefore, the useful output of hydrogen is 472 mole per second, which is also equals to 30,000 tons per year. And also the total input of H2 is gained from the inlet stream, which is stream 1, which is from the feed of the stream which is 962.375 mole per second, times with the composition of 0.491. Therefore, we get 472.5 mole per second. As we calculated, the efficiency of H2 production is the same as the question needed, which is 99.9%. Therefore, as we conclude that the assumption and also flow rate stated from the beginning of this process, from the reaction engineering process till this separation process of H2 production, are acceptable. Lastly is the desorption or regeneration process. In this process, in the PSA process, gas is compressed to a pressure between 4 to 10 bar and is fed to a column where it is put in contact with zeolite that will selectively retain CO2. The absorbent has a characteristic of porous solid, normally with high surface area. The purified H2 is recovered at the top of the column with a very small pressure drop. After certain time, the absorbent is saturated with CO2 and the column needed to be regenerated by reducing the pressure where the column is fed with the reformed gas at low pressure in order to complete the absorbent bed regeneration. Before the regeneration happens, equalization step takes place where the column is partially pressurized with the high pressure gas withdrawn from another column. It will be pressurized firstly with recycled stream and then with the reformed gas. Therefore, in this desorption or regeneration process, the regeneration phase will consist of 5 consecutive steps, which is the first one is pressure equalization, second one is provide purge, the third one is dump, and also the fourth one is purging, and the last one is repressurization.
That's all from us, and thank you very much for listening to us. Have a safe day.